Let statement P denote Raj does yoga regularly. And statement Q denote Raj's blood pressure is normal. Right? Now, don't you think P implies Q is true? We are revisiting P implies Q. If you remember, P implies Q meant it will not so happen that whenever P is 1, Q happens to be 0. This is never possible. Right? When P is 1, Q is also 1. Then you say the implication is always true. Correct? I repeat, look at the truth table of P, Q and P implies Q. 0, 0 is 1. 0, 1 is 1. 1, 0 is 0. 1, 1 is 1. The only situation where it is false is when P is 1 and Q is 0. Then P implies Q becomes false. That statement becomes false. You see, now, is this statement true? P implies Q here. Very true. Because you observe, logically speaking, if you are physically active, your blood pressure remains normal. Okay, most of the cases. Let us assume this to be true always, right? P implies Q is true. Now, look at this. But does Raj do yoga regularly? If P is not true, if P is false, you cannot say anything about Q. But if P is true, you know for sure Q is true. Because P implies Q is true. Now look at this. If P is true, given that P is true, and if P implies Q is true, you can conclude that therefore Q is true. Observe this boxed stuff deeply. This is not in particular about the given example. In general, whenever you say P implies Q is true and P is given to be true, you forcefully should conclude that Q is true. Now, it may take some time for this idea to sink into your mind. As and always, you should solve a lot of problems. Don't worry if you don't understand what I'm saying. What I'm saying might even sound ambiguous, but let us solve some 5 to 6 problems. And at the end of these problems, it will be very clear to you what we are doing. Okay? We have solved questions with implication being our final inference. Now, we'll try to show this question with 4 statements and one final inference, which is therefore R or S. We have to show that R or S is true. Now, the same old trick. We'll try to show this by contradiction. What do? We'll assume R or S is not true, which means R is false, S is false. The moment you say R is false, I'm going to spot all R's and make them 0. You have 1 in the second line, 1 in the third line. And then S is also 0, so I put S as 0, 1 in the second line and 1 in the first line. Okay? Perfect. Now, you see that, look at the first line. S is false. First line says not P or S is true, which means not P should be true, which means P is false. Okay? So P should be false everywhere. You see, P is false. Fine. I make P as false in the 4th line, as you saw. Right? Okay. So P is false. And now R is given to be false. Not Q or R is true. So Q has to be false. So I put Q to be false and I put Q to be false in the 4th line as well. Okay. Now look at the second line. S is false, R is false. S and R becomes false. And not T or this. Second line. Not T or S and R is true. Right? But S and R is turning out to be false. So not T should be true and hence T is false. So T is false. Look at the last line. We have a contradiction. P is false, Q is false, T is false. But you're saying P or Q or T is true. That's not possible. So contradiction to our assumption that R or S is false, which means R or S should be true. and therefore RRS is our answer. I'm sure you people are getting a hang of it right now. Look at this question. I got to show that T is true. It's slightly tricky. How do I go about it? Now, look at the first line. It says not P and Q is true, which means Q is 1 and P is 0. Only then will not P be true and not P and Q be true. Okay, so P is 0. Look at the second line. P is 0. Something which is true cannot imply 0. R implies P is true. So R has to be 0 only. If R becomes 1, 1 cannot imply 0, which is P. P is known to be 0, you see. So R implies P. I very well infer that R is 0 here. So far so good. If R is 0, not R becomes 1, the next line, correct? If not R is 1, and this 1 is implying something, that something should also be 1. So S is 1. Perfect. S is 1. S implies T. So T has to be 1. So I can conclude that therefore T is true.